Hello everyone, welcome to today's webinar. Thank you for joining us today. This is for enhancing grid resilience and visibility at the edge for SmartLV solutions. My name's Lisa and I'll be your moderator for today. We've got a great presentation lined up from Guido Voigt from Lantronix, and we're looking forward to sharing some valuable insights with you. Just before we begin, I'll run through a few quick housekeeping points. You'll notice that all attendee microphones are muted. This is to reduce background noise. All of your webcams are also switched off, just to make sure we keep connection quality. We also ask that for any questions that you add them into the question Q&A chat. Please feel free to ask questions at any time using the chat box, and then we will have time at the end to cover those questions. And also we are recording the webinar so that the session can be shared with attendees afterwards. Next slide, please. Thank you. Moving on to talk about why we're here today and what you can expect from the session. This webinar is designed to help customers explore the growing opportunities in smart low voltage applications. As energy demands increase and pressure on current infrastructure grows, it's becoming critical to monitor and manage LV networks in real time, along with the ability to predict any issues before they cause outages. Our team at ACAL BFI are committed to helping you find the right solutions for these challenges. And today we're pleased to be joined by our partner Lantronix, who will showcase a powerful solution and addresses the real world challenges in LV infrastructure. We will finish at the end with a Q&A session. So again, please send your questions through the chat at any time and we'll address them at the end. And with that, I'll hand across to Guido, who will kick off today's presentation.
Yeah, hello everybody. My name is Guido Voigt. I'm the Senior Director of Advanced Development from Lantronix and working on that topic for some time right now. So we want to present here our Smart Edge SmartLV product, which is one of the first AI-enabled edge compute gateways in the market. Let me start a bit with about the topic overview and our vision on the problematic in the low voltage substation monitoring use case. This slide is maybe the one where hopefully talk most of it. That shows a bit the situation what we have right now in the utility market in the low voltage substations. There is a traditional architecture of the power grid worldwide, more or less, mostly here on Europe. Where we get the energy via the long transmission lines, via the high voltage power lines, which is 100 to 200 kilovolt with long distance, and then that transformed to the middle voltage, which is about 30 to 10 kilovolt, and that's normally what is reaching the low voltage substation. So you see the energy coming inside here, and then you have in the local grid somewhere some kilometers away from your house or from your office, you have such a low voltage substation, and they transform the energy from 10 kilovolt, 30 kilovolt down to the 220, 250 watt, what you know from the past. So, and on that one, there are the cables connected to the offices, to your home, even to other small fabs or generation facilities like a solar plant. This small substation normally covering about 300 households nearby, and they are very essential in that market. This was normally done and architectures calculated and dimensioned from statistic over years. But the world has changed. So in the last time, you know that we have a higher demand of energy. Especially in that field. So in the earlier times, we had only used the energy, electricity for lamps, for maybe putting on the TV, the washing machine. But in the last years, we have specialty the higher demand of electrical cars, what we want to charge. We have heat pumps on our houses to heating up the house. We're having solar panels on the roof to generate our own energy, and that energy is going back to the grid up to the other network. So that demand has made the energy transportation much more fluctuant. So it means you cannot really predict how the energy flow, and even the peaks of that consumption and the generation, they are much more flexible. So, and that is a problem. In former times, you have a household, something like that, we have an average power consumption of 1 to 2 kilowatt, more or less. And now, if you are adding a car, where normally the maximum peak consumption of charging a car is about 11 kilowatt. So 11 kilowatt compared to 1 or 2 kilowatt is factor 10 to 5. And this is something which can cause that you have an overload in the grid. Not in a single point, but if everyone, let's say in your street, start doing this, then you are reaching the limits what you have in the low voltage substation as a default of limit. And what you have to prevent is, in each of the substations there are fuses in. That's something what you can see here. So each of that blue parts what you see is their own fuse. The energy comes from the transformer, which is here on the on that side, and the cables to your home is going out here on the bottom side. So it means if you have there a too high peak, then that fuses go off, and someone has to go there, figure out which fuse is gone, replace them, and switch it on again. To prevent that, and that to see even how that system behaves, there are some different regulatory requirements in the market right now, where it asks the DSO, that's the power distribution organizations, to monitor that low voltage substation. And that's exactly where we want to talk about how to put devices in, how to power meter and measure the condition of the substation and the grid below, and how to transfer the data. So that's the real challenges what the DSO facing right now in the power distribution. We have much more renewable energy, so it means the energy not going from top to down. There are even the energy coming back from local power generation. It could be solar, it could be wind, it could be even other generation like from bio power plants. We have an increasing demand. So I have an extra slide for that, where we see that we are using energy, but we are using energy differently. We are reducing the gas consumption, we are reducing the fuel consumption in car and moving that to electricity. So it means we are putting energy from other transportation to the transportation of electricity. So, and to understand how that works, to prevent malfunctions, to prevent failures, and to improve the maintenance, we have to read and we have to analyze the low voltage grid. And even when we are doing it, it's very, very important that we're taking care of security and safety. This is a critical infrastructure, so even when we monitor and control that system's remote, we have to make sure that we don't have any cyber attacks, and that the system is stable even when parts of the system are failure. So that's what I showed. Sorry that there are some things in German, but that's what I copy out of an official document. So what you see here right now is this is at the end the power consumption of Germany in 2023, put in different sections. So what you see, that's the industrial, that are the private households. This is local offices and trading organization, and that is all the traffic what we have. I know that the colors are not nice, but this colors here, what I put here, that's kind of red pink. This is the energy consumption by electricity. This is gas, and the blue one is oil. So think about that. If we are moving our complete traffic system, it means the trucks, the cars, from the fuel-driven one here, which is right now electrical only. That part, if we put that together, this energy has to transfer. We are the same kind of grid which we are using only for that. And even the industry, maybe not so much, but the most of the households, they will start moving from gas heating in Germany to electricity moving. So even that part go pink. So what you have to see is we are maybe reducing in total the energy consumption in Europe or in Germany, but we are moving that from other transportation and energy systems to the electricity. And that is a challenge what we have to cover. So what are really the benefits when we are monitoring the substations? Very, very important is fault detection. So it means if there is no energy anymore at one place, no one has to call someone, hey, I don't have energy. Something like that has to be monitored in real time. It means all the DSOs, they're having big centers where they monitor their system, and then they need to see, okay, in I don't know, substation ABC or in that house, there is no energy anymore. So we have to do something. So we have even diagnostic. We're having much more very different power consumption devices in that system. Many of them even generating energy, and they are not using it traditional way. So some of that system can influence each other and generate a non-needed artificial high load, and that can cause a failure, a fault, a disconnect, or even a disturbance, which can even, let's say, burn down a substation. That is something we have to prevent. So when we have the real-time data, we can run that diagnostic and we can create predictive maintenance. What we mean with predictive maintenance, we are seeing that, let's say, some part of the grid are degrading, but when we are seeing that we have caused a specific limit and we trigger them, then we can send people before the fault can happen to repair or maintain that part to really reduce the number of failures in the grid. And that's becoming much more important in the future. And for having that, we need to have really real-time data visibility and get that data very good analyzed. Then we have to optimize the efficiency, and we optimize that. So especially we need to know in which area currently energy is more produced than consumed to see and to understand the load of the power generation in the traditional power plants. Operational control is, again, we have to see where are my substation, what is connected, what is my power consumption, to make a plan how to generate and how to architecture future grids. What is that important as well is when someone build up a new house in a road, the DSO has to check if he is able to even connect that new building to the existing grid, or that has to be upgraded. So, and if you do that on very old statistic data, that can cause a failure. So you have to analyze that in reality and see if the statistic done over complete Germany or Europe is a statistic which is even has the cause in that road where that guy has want to build his own house. And then very important, it is the last in line, but I expect that that's the one why the people will start or have to start using monitoring like SmartLV is the regulatory compliance. So there's a European-wide law out, that's the Electricity Directive 944, and in Germany that is the setting of paragraph 14.8 in the local state law, which require the DSOs, means the people they are transferring and the energy down to the house or to the office. They have to monitor the substations. They have to monitor the quality of the power to have a resilient grid available for the people. All right, so that's what I'm talking is about, what we see, what is the market needed, and currently how we see the challenges and the benefits of that. So we talk about right now about edge compute, and some people may don't know what edge compute means. That's why I have a slide here to explain a bit what are the benefits of edge compute. First, edge compute is the compute what you don't do in the cloud. That's the edge, that's the compute what you are doing more or less after you have an acquisition of sensor data, you have the data, and before you transfer the data to the cloud over any kind of data connection. The data connection in our case can be a fiber cable, which is maybe not the big problem because fiber cable can transfer point to point a very high number of data with to a normally small cost. But some or most of the system will connect that data even whether as fallback or as primary connection via cellular data. It means via the normal cellular network. And that data has some limits in bandwidth and speed, and of course has a very high cost. So, and that's why the idea is to compute the data. It means to analyze the data you get in locally on the device before you communicate and transfer the data over the WAN, the wide area network. It means the long distance where it can cause bandwidth and cost. That's called edge compute. The benefits of edge compute are specifically the latency. They are very low. What it means is if you send, let's say, a sensor data via traditional thing, you acquire the data, you put it to a gateway, and you send that data via cellular to a cloud, and you have the data there. That transmission is mostly more than 200 milliseconds. So, and then you have to compute it in the cloud, and then you want to send something back, and so it has the same way back. So at the end, you are on, let's say, something like 500 milliseconds or 1 second. That is maybe not a very long thing in your normal life. But let's say if you want to prevent that the switch has to go off because there's a malfunction, 500 milliseconds is a lot. If you do that in the cloud, then we are talking maybe of the transportation of maybe 1 or 2 milliseconds to the edge. The acquisition and compute time is maybe the same. So it means we can normally react on that stuff in 10 milliseconds. So that's the factor of 10 to 20 and even more in reality. The scalability on edge compute is a bit limited because normally you have only one device at the edge and you can have the demand in the cloud, how many money you pay to one of the big cloud offers to have their more compute power. So that's one part. The cost and the cost here, I really divided that in initial and long-term cost. So of course, the initial cost in the edge compute is a bit higher because you have to buy the device and the device need to have the capability for compute. So that's why this is medium. But long-term, it goes low. What I mean with long-term in a second, because on cloud compute, it's low. The only thing is you get the data, you pay the CPU time, that's low. But you pay that each day, each month, each year, or 10 years. So if you think about that, an edge compute system is normally organized and architectured that it should run 10 years plus. You pay them once, but you don't really pay the compute power there. You pay the power, but the power at that point is even cheaper than in a data center. So it means normally in the calculation is an edge compute system normally pay out after the first 6 months to 1 year. And means long term, if you go for 10 years, the cost is much lower on edge compute than compared to a cloud system. Then, of course, you have a bandwidth performance. So the bandwidth is much lower because you are, if you do it right, you get all the sensor data and you, let's say, make a filter where only you change the delta of the data to the cloud if you want to do the cloud compare. So with that one, you have a data reduction by more than 90%. So you only send 10% of the data upwards. And you can even do it more if you run the data analyzers directly on the edge, which you can do with a SmartLV. Then you analyze the data real time and you only transfer anomalies or malfunctions or faults or notifications that you see something in the data, and you don't send all that data to the cloud. And with that one, reduce the transfer cost of the data a lot. Privacy and security. So the good thing here is on the compute, the first stuff on privacy is all data you don't transfer or put in the cloud are much more safe because you don't know what happened with them in the cloud. If you generated data, that's a small first privacy problem, and the next privacy problem is if you store them. If you generate them, analyze them, and don't store them, then of course you reduce the risk of privacy faults. So that's why the ideas of generating a lot data. So even if you are sampling the sensors in a much higher frequency, where you even see much more things, how people use the networks. You can do this if you analyze them, don't store them, and only things where you have really the need on it. You see a malfunction, you see something abnormal, and you take that small snapshot of data and you send it to the cloud. You reduce the privacy a lot, and the security there's as well, because you don't want to see so much data traffic, and then you can see even then you have security faults in it because you have an abnormal data traffic. Offline capabilities. What I mean with that is that's one of the biggest problem on resilient of such critical networks. You have different components inside, they can fail. What can fail here in that system? The sensor can fail, the edge compute can fail, the gateway, the data transmission system can fail, I mean the cellular network or the fiber network or the cloud. To be clear, if the cloud failing in the cloud compute system, you don't get the data, you have a loss of data, you can compute them, nothing happen. If the data transfer network is failing, then cloud compute can still work on the existing data, but they don't have more data anymore, and even they have no way to remote control the system. Then, depending on the setup, they can retrieve the data later on if the connectivity is there, if they have a higher advanced gateway which are store and forward the data. On edge compute, it's so that even if the cloud is gone, even if the network is gone, the system can even analyze the data. It can create still the snapshot. It can still create the anonymity and the notifications. It cannot communicate them, but it store them and wait that the connectivity is coming up, and can send that data afterwards when the system is up and running. If you have the full control system run on the edge compute system as well, it even can react directly on faults detection, let's say switching something on and off. The maintenance, of course, that systems are higher because you don't have them localized in one point like a data center. So they are directly on your substations, but your substations you have to maintain as well. So it means if you do that, the maintenance of the edge compute in the same way, then you maintain your substation. That is something valuable and not an extra cost on your system. The cloud compute win here as well because it's a lower cost and centralized. So here again, for you later on to read out the compute benefits as a highlight. And the next slide show a pro and con on each of the systems. So most of them, I guess I taught right now. That slide is more for you to read later on. Okay, so talk about a bit Smart Edge and SmartLV, the device what we have. So we have a platform called Smart Edge gateway solutions, and SmartLV is one of them because that device is specific designed for the need of utilities, in that case on low voltage substations. So that's a small device which is a gateway as well, has compute power inside, has Wi-Fi, BLE, has a fiber system, 4G and 5G as an uplink, has all the interfaces to read local sensors and be able to compute them. The other use cases for Smart Edge is industrial automation, computer vision. You can put a camera on it, count the number of cars running around. So I will not go much more in detail of that. So this is a bit how we see that device. So the device is at the end, directly in the middle between the sensors, what we want to read out, and the systems we need to analyze and control the data. So that's what we have on the left side. So we are sitting in the middle on the edge. So we are reading all the sensor data with that device. We can locally analyze the data really in real time. We can run software on that device, so you can define what software have. Think about you have an own PC built into that system, which can read all the sensors and can transfer the data to the data centers. And so you can even run AI software on it, which can figure out on the data if there's something unknown, means that device is connected not anymore. That device send all 2 hours much more data than usually. Or let's say you see that at one specific time you have an overload or no connection on one of the sensors, and that data You have notify, you sample the data, send up, and someone can check why that happened and if there is a fault in the system or the system needs to have maintenance. So that is something what we put in the middle, and it replaced normally traditional things where you have a data acquisition system, then you have maybe industrial PC in the middle, and you have a traditional gateway which transfer data. We put that all in one device to reduce the cost, optimize the speed, and the handling of that system. So that's the primary idea of a SmartLV system. Okay, a bit about the architecture. Let's talk about first what is in that device. So we have currently discussed two SKUs for that. So it means two variants. One of them will have internally a so-called IQ6. That's a bit smaller microprocessor, and it will have the 6490, which is a higher performing processor. So from a normal compute, they are the same, but they are different. One of them have 1 TOPS and the other one have 40 TOPS. What it means, TOPS means tera operations per second. That is AI calculations. So as higher the number, as more AI calculations you can do in the same time. 1 TOP should be good enough for most of the sensor data analyzers. 40 TOPS you may need when you need to analyze video data in a high speed with multiple cameras. So we have about 2 to 8 gigabyte RAM. We have standard-wise for all the system 120 gig UFS in the system. It will run Linux on it. We have all the RTC watchdog and TPM system for high reliability on the system and very high security. So the TPM, that's a trusted platform module, which is certified and give you the conformity that we can store data like certificates in a very secure way, and that all our cryptographic algorithms we have are certified and not be able to compromise. On the radio system, we will have Wi-Fi 6E in it with working on 2.45 and 6 gigahertz. We have BLE, Bluetooth Low Energy in it. That's mostly that they can communicate with maintenance guys when they are near the station. We have GNSS inside. That's there that we have a very high correct timing into the system. We have a second M.2 slot in it where we can have any other local wireless private area network, so like LoRa or Sigfox or something like that, you can put into the system. Some substations use that because they have other sensors that are connected to the substation and they want to read out. That's why that option will be there. And we have cellular on it connected with M.2. So primary, we guess that the 4G Cat 1 system is good enough for that, what is needed. A lot of Europe DSOs, they're using 450 megahertz, compliant to the 450 megahertz alliance that will be supported. Long term, we expect that 5G RedCap is the right way to go. Currently, we have in that device a full featured 5G modem for all the POCs to be able to figure out what is the real speed on the system, and that's what we have in the current devices for testing. We will have one-time gigabit Ethernet LAN port with PVPD. That's normally for the uplink, so you can power the device even via that port. Then we have 2 times Ethernet local, and they are supplying the power on the Ethernet as well. So that's perfect. If you connect, let's say, 2 cameras on it, you can power the cameras, you get the data in real time if you want that. Additionally, we have a SFP port in it, so that's mostly for different fiber formats. We can connect that for the WAN port. We have CAN-FD inside, so that will be there for some use cases for power storage. So CAN bus is normally the standard protocol there to control and read out the data from the storage. Then the traditional one to read out all the Modbus, the standard power meters into the system. What we have there, AUS 232.442 and the 485 for Modbus, that will be there in isolated, and you can program which variant you want to have. Specific wake up, that's follow power functions and in and outputs. A USB-C, some USB-A. So even on USB-A, you can have your own equipment connected. We have a mini DisplayPort and HDMI that for some use cases where you need to have a local displays, some requirements can be there for some local law. That's why we have it inside. We have an internal and we have an external SIM, and the external SIM is a 3-in-1 system for SIM and SD card when you want to store something. Again, the second M.2 from up where you want to put your own low wireless network. And we have another M.2 card inside where you can have extra storage SSD for security, or if you want to store much more data than the standard device needed. To give flexibility for different use cases, we had some stuff extra in it. On a software point of view, it will come with a real-time operating system based on Linux. We expect it will be a fully Yocto compliant Linux. Why Yocto? Because you can strip it down for security, that only really needed software is on the system and not there's no software you don't need on the system. That reduce security risk because most of the security problems or ways to go in are software you don't normally use for your use case. We even offer the use of perception, which is a telemetry and firmware update and configuration software from Lantronix. That is an optional thing you can order. We have container management in it. We have the edge compute capabilities. We even have AI machine learning pipelines integrated already you can use. We offering an own package called InfiniShield. That's a strong cybersecurity stuff. So it means when you activate that, that will check the traffic, it will fingerprint the traffic, and if it see there suspicious access to some of the components, it will send notification or block that access. The system will have a lot of VPN pre-configured systems on it so that you can send your data to any endpoint you want. We have the industrial protocol conversion suite. That's an extra slide coming. And user scripting and SDK will be available. You can power that device with PoE, PD, or you can power it with an external plug from 12 to 56 volt. That's for the hardware. So the protocol conversion, what we have. So we have real-time conversions software on that system. It's an extra package what we supply. So on the left side, that's all the data normally we can read via the interfaces. So that's the input part. Then we have the compute part where we can convert each of that data to each of the output protocols. And at the same time, we can even put them in an MQT broker, in an SQL database, or on storage, or the same data we are putting in an AI machine learning pipeline to generate more data out and to send that analysis even to the output protocols to your backend. Okay, a bit on the demo. I hope I'm good in time. So that's one of the demo what we've done. It's always a smaller problem if you go to an exhibition that it's very hard to carry a full substation with us. So we try to optimize that stuff a bit. We put a small simulation of a substation here into that box. So what you can see here, there is the SmartLV in it. Then what we put there as a standard power user, it's a simple lamp. So that is a power consumption system. Then we have the one which should, let's say, show the more higher demand, which is here a hairdryer. It's not because I have long hair, but it's the easiest way to find. To be fair, the first one I used from a hotel room because I forgot mine. And then, of course, we have some sensors here, and that's why these are so-called Rogowski coil sensors. That's something how you can measure the energy you have. And then only to show that we can generate and have the real-time data, here's a laptop, and the laptop show only a browser GUI from everything which is running directly on the SmartLV. So for that one, there is a link at the end of the presentation where you can click and you can see that demo fully running if you want later on. So here again, a bit how that system is normally happens. So you have the SmartLV here inside. You have a power supply. So we have the biggest power supply here for the PoE function of the SmartLV. We have a smaller power supply here for the power measurement device that we have inside here. Then we have here a bit the wiring part only. We have some switches and we have some power controllers connected with Ethernet or Modbus to the SmartLV. And here what you see is we having here the built-in smaller Rogowski coils to read out the energy. Here we have 3 standard sockets. They should simulate the 3 phases normally you have in a substation. All right, another demo, what I can show here, which I don't have as a link, it's a demo what you can do besides the usage of reading only the power data out of the sensors. So I need to switch here something on. So this here is a demo where we want to show that one of the easiest sensors you can put in a substation is a thermal camera. So this one here is a very cheap one camera. Lantronix even partner with FLIR, and we made for them even AI in their cameras. And so some of that use cases you can do with that camera, or you can do with any other thermal camera combined with a SmartLV. What you will see here is that's a picture of the coffee machine in my office. So this here is the coffee machine. And let's play the video and you see and I explain what's going on. I hope that you can see the video as well. So at first you see nothing. What I done, I press the button here, make me a coffee. Okay, so when I press the button, make me a coffee, the coffee machine will start up heating up the water inside. And the first thing is AI detecting that there's some abnormal things happen. And then what you see here is that there's something heating up. So again, it's not heating up that it's really glowing. So what you see the difference here are maybe 0.1, 0.2, 0.3 degrees more than the environment normally before. So you can touch it, it will not hurt. But that's what you see here right now. That's the cable of the coffee machine. So think about, you have a lot of cables there inside, and normally they are warm or not hot, but they are warm. But short before they burn through, they will have to go very, very hot. And if you have a thermal camera, you can put a very low trigger on it, so that even when it takes time before they burn through, you have time. And the time can be 1 hour before, 10 hours before, when you start detecting that there's something not good. And that's something which is exactly the predictive maintenance use case. So at the end, you see right now it even detect now something more, because even now my coffee machine is really going hot. And each of that detection is that you send an information back to the system, maybe connected with the picture and the detection. So the good thing here is you can have real-time video, really with a high resolution, but no one has to watch it. The AI watch it and only send you, here's something happen. And hopefully it's happened only once or never in 10 years. So no one has to watch the video, and you don't have to stream that video to the cloud. And such a video can have easily 2 to 4 megabit per second data stream. So and that can cost a lot of money. First in the transfer on the seller, so you have to pay them. Then what you do with the video, you store them or you analyze them in the cloud. If you analyze them in the cloud, you pay for each second the compute power in the cloud to analyze them. And if you do that on the edge, you don't have that cost on your bill. So that's why we expect, and our view is that edge compute will solve that problems for a much better cost than to do that analyze into the cloud. Okay, that's the demo. So then we have some use cases. I guess some of them I already discussed. So the standard use case is the SmartLV substation monitoring use case, where we have that substation. You saw the pictures here before. Here you see again the cables, they are going out, and that's the same cables what you have here. On that cables we have connected the power metering hardware. We have some more slides coming later for that. They are connected to the SmartLV, read them out with Modbus. We analyze and compute that data. We are sending the data via the cellular network or with fiber networks to any IoT platform. And on the IoT platform, normally connected is the DSO EMS. EMS is the energy management software, where they have their plan, their grid plan, and they want to see which of the substation, which grids consuming or even generating what number of power. The key points for that is really make sure most DSO, they have to be compliant with that electricity directive in the EU. If they are in Germany, that's the local state stuff. I don't know right now the laws which are in the other European or international countries, but I'm pretty sure in all European that has to be a local law as well. And I know some other countries are following that stuff as well. So in that use case, we have really an effective monitoring. We even have control channel backwards. So you even can send something to the system and say, hey, switch off that grid or restart that switch and something like that. That's even there and working. So that's that use case. And I would like to ask now Eric to go a bit and give some information about that specific power metering and power measuring devices which we are using from ACA.
Okay, thank you, Guido. So my name is Eric from ACA BFI in Germany, in the sales of technical, in the role of technical sales director in the comms division. So in the previous slide, you saw the use case of the monitoring the transformer station, and where the voltage and current meters are connected to the SmartLV edge computing device. I will now introduce you the voltage and current meters, which is in combination our modular power meter in more detail. The modular power meter consists of a voltage, volt 1000, and current meters with a Modbus interface. You can see the voltmeter, the volt 1000, on the left, and the current meters connected to the volt 1000 on the right. The elements of these systems are the voltage module, the volt 1000, that measures L1, L2, L3, and N, and up to 20 current modules that measures power and current. In other words, for up to 20 three-phase plus N outgoing power lines, it is possible to measure the voltage, current, and power for three phases and the voltage and current in the neutral. To accomplish this, the volt 1000 meter samples the voltage and sends the samples to the current meters on the cascade bus. Each current meter uses these samples to calculate the power. The volt 1000 meter acts as a bridge between the Modbus master and the cascade bus. Only one cable needs to be connected to the RTU master, in this case to the SmartLV device, to measure up to 20 by 4, what means 80 power lines. We offer some variations of the current modules. Now, keep the previous slide, please, Guido. Yeah. Our so-called ROCOS current sensors with the Rogowski coils are available in two versions. One with a 65 mm diameter coil and the other version with a 110 diameter coil. The other current sensor model, called Cube, has a different form factor and is designed for cables where the distance between the cables is low as 4 mm. This is what you see on the right. Yes. In addition to the volt 1000, which you can see on the left, we also offer the volt 1000S as an alternative version of a voltmeter. I will tell you more about this on the next page. The volt 1000S is an alternative voltmeter in a different form factor for DIN rail mounting, with basically the same features as the volt 1000. Nowadays, power quality becomes more and more an upcoming issue and therefore a requirement to measure. Why is power quality important? Industrial systems can be disrupted or damaged by poor power quality. Electronic devices react sensitively to voltage distortions or dips. Energy efficiency and operational safety depend heavily on a stable power supply. New is the feature now that the volt 1000S supports power quality measurement. And the parameters which are measured, respectively detected, are frequency variation, voltage dips and interruptions, temporary and transient overvoltage, voltage imbalance, voltage harmonic distortions, and vector surge. The unique selling points of our modular power meters are: the system consists of only two components, the Volt 1000 and the ROCOS or cube meters. It's easy for ordering and stock keeping. Minimal time required for installation and commissioning. Up to 20 meters can be cascaded using standard patch cables. No extensive installation or installation training is required. Minimal wiring is required. That means it's an accident prevention. And it's a robust design with a touch surface and display for measured value indication on site. Modular design, especially designed for retrofitting for transformer stations in the field. These units are developed and produced in Belgium. That means it's a European product. That's so far all from my side, and I will hand over to Guido again.
Okay, thank you, Eric, for that. Again, maybe for other information, that measurement stuff you can get directly from ACAL, so talk to your salespeople there. All right, so then let's go to the next slide. So I have two other small use cases for that. So one of them is EV charging station. So as we have even display in that, and we have the input for this USB, you can have even a normal keypad connected. You have a display connected. We can measure the energy consumption. We have everything inside, even to read with RFID or credit cards. So you can have an easy setup for an EV charging station or for any other point of sale system with SmartLV as well. That is one of the extra use cases. And then one of the standard use cases is, of course, even solar or even wind turbine power monitoring. That is not in the substation, but exactly the same number, same number or same type of sensors, the same type of use case, only a bit different setup. So we can have the device and data management on the system. We can measure per panel, per inverter, or even per battery, because the new thing is that they even put storage near or under the solar panels. We can see if one of the batteries maybe not performing. We can read out of some of the panels maybe don't have the good quality anymore, and to replace them. You can even directly generate the power numbers and invoicing that system. We have even connectivity service and SIM cards on it. So that's exactly the other use case. I jump over it because we are running a bit out of time, talking a bit too much. That's why even we have here a bit the takeaways from that session. I don't go through because we named them all here inside. I guess we shared a presentation afterwards, so you can read that out in yourself anytime. Here a bit more information on it. So there's a SmartLV web page on Lantronix. There is another a thing on check our Lantronix LinkedIn page, because there we see all the news, everything what we are doing on it. Then there is a link to the video where we show the demonstration even a bit longer. And there is another page from BFI about the power meters Eric showed you here. It's currently in German only, but I guess everyone know how to automatically translate that in the browser. Then a small thing about the acronyms we use. I don't know if some of you don't know them. I put them here as a small list in it. You can read through and figure out what's going on. That's my thank you, and I guess we're coming right now to the Q&A session, and I hand over to Lisa again.
Thank you. We have got a couple of questions come in. One saying, perception is not an edge SW, or is it? software, I'm guessing that is.
So Perception is a cloud software from Lantronix, and that is made for even controlling and managing all the devices from Lantronix. So you can connect to Perception all of the Lantronix devices. It could be a telematics device, and it could be even the SmartLV, and you can see the state status of the device. So if it's online, if it's offline, you see the version number and so on. And very important for Perception is that you can upload and download the software you want to run on it, and you see if the system is healthy on that. Perception even can acquire all the data you want to have and give it as an API to your backend system yourself, but this is only an extra additional function on it.
Next question is, when will the SmartLV be available?
So our current plan for that is that, let's say, until end of the year, we are really focusing on customer POCs. So we have devices available, which is from us internal code POC level, where we go with dedicated customers in proof of concepts. And we have right now for more a year the system running at some DSOs. The public availability and mass production we expecting to have end of the year and the rollout to customers in Q1 26.
Next question, what is the power consumption of SmartLV?
So that is a really a benefit. I didn't mention that in the cases here before. Such a device right now, let's say connected with 4G in let's say a kind of idle mode, running a small number of software on it, which means the demo itself. So on the demo, there's AI running, MQTT broker running, and REST API running to present the data. There are 5 devices connected, and the Wi-Fi hotspot is running. We are below 10 watt in total, which is quite good if you compare that to a system where you have a gateway and industrial PC, but not because normally industrial PC and that stuff itself minimum taking a 20 to 90 watt and the gateway in the same kind like what we're having right now in 10 watt. So we are quite power efficient that based because we are using Qualcomm CPUs on it, which are made for extremely low power. That is one of the key benefits from SmartLV as well.
And next question is, can I have a full demo?
Yeah, so full demo, it's something, our plan is that everyone who wants to do really a project with that system, who can order an evaluation kit, which normally contains a SmartLV, all antennas, all power supplies, everything what you need to bring that system up and running on your desk. And in that kit, there's even 8 hours free support included, and even a 4-hour consulting / demo session is included as well.
And the last question we have is, what is the cost of SmartLV?
So we did not have really a final cost calculation done for the market, but we really want to be very, very aggressive. What means if you see right now that industrial PC is normally below $2,000 something, and we want to have that system really aggressive in the market. So depending on with cellular, without cellular, what kind of CPU we have inside, we want to be, let's say, in the range of $1,000 and below.
Lovely, thank you very much. I think that's pretty much it for today. So thank you to everybody for joining us. We hope you found the session insightful and that it sparked some new ideas for how SmartLV can support your projects. If you have any further questions or would like to discuss this application or want to explore any solutions in more detail, please get in touch with us. We have our contact details on the next slide. Thank you. And that's it for today.
Thank you very